In this video, we're going to finally start talking about how spinors are used in particle physics. The area of physics that helps us understand fundamental particles is called quantum field theory, or QFT. Now, QFT is an enormous topic, and it normally takes 3 courses at the graduate level to cover the basics of it. There's no way I can cover all of QFT in this series. Instead, I'm going to cover just a small sliver of QFT, which is the Dirac equation. The Dirac equation is the equation that governs the behavior of free spin 1/2 particles in the absence of any forces or interactions. This will hopefully give you a sense of how spinors are used in the larger topic of quantum field theory. However, before I get to the Dirac equation, I'm going to use this video to give you an overview of quantum field theory as a whole. I'm not going to go into a lot of detail, but I'm going to try laying out a general map of QFT and show you how the Dirac equation and spinors fit into it. So frequently, I see quantum field theory as being composed of 2 main sub-areas: particle physics and condensed matter physics. I'm not sure if everything in QFT belongs to one of these 2 categories, but these are definitely the 2 main sub-areas. Particle physics involves the collisions and interactions of particles. This involves the study of things like a photon scattering off an electron and its antimatter counterpart, the positron, annihilating into 2 photons, a neutron undergoing radioactive decay into a proton, electron, and antineutrino, or quarks being bound together into protons and neutrons through gluon exchange particles. Particle physics typically involves a relatively small number of particles, so that you can keep track of all the particles individually. On the other hand, condensed matter physics involves the collective behavior of a huge number of particles. The number of particles is so huge that we don't normally keep track of individual particles, and instead we look at the statistical behavior of particles together as a huge group. The collective behavior of a huge number of particles is what lets us understand the states of matter, like solids, liquids, and gases. These states of matter are not really programmed into the fundamental laws of physics. Instead, states of matter arise out of the collective behavior of particles together. Condensed matter physics also allows us to study more exotic states of matter that we don't normally see in everyday life, such as Bose-Einstein condensates and superfluids, and it also lets us study superconductivity. So quantum field theory lets us understand a lot of things, but what exactly is it? You'll often hear people say that QFT treats particles as excitations in various fields. For example, electrons are viewed as excitations in the electron field, and photons are viewed as excitations in the photon field. But what exactly does this mean? To understand this, I'm going to draw a bunch of areas of physics in a cube shape. In the starting corner of the cube, we have Newtonian physics. From here, we can expand out in 3 different directions, using special relativity, quantum mechanics, and classical field theory. If we try to combine quantum mechanics and special relativity, we get relativistic quantum mechanics. This theory can help us predict some things, such as the existence of antimatter, but as a whole, the theory is kind of broken and inconsistent. To save it, we need to use field theory. If we combine quantum mechanics with field theory, we get non-relativistic quantum field theory. This can help us understand some of the condensed matter systems I mentioned above. However, when it comes to particle physics, where particles are usually traveling at or close to the speed of light, non-relativistic QFT fails because it doesn't incorporate special relativity. If we combine field theory with special relativity, we get relativistic field theory, which lets us model fields where waves can travel at or close to the speed of light. But this does not obey the rules of quantum mechanics. Finally, if we combine quantum mechanics, special relativity, and field theory together, we get relativistic quantum field theory. This is usually what people are talking about when they say QFT. So to properly understand quantum field theory, we need to understand special relativity, quantum mechanics, and classical field theory, and understand how they all fit together. So let's start with special relativity. The two postulates of special relativity are that the laws of physics are the same in all inertial reference frames, and that the speed of light in a vacuum is also the same in all inertial reference frames. What this really means is that we need to change from using the Galilean transformations from Newtonian physics and upgrade to use Lorentz transformations. For Galilean transformations, time is universal in all reference frames, and position transforms with basic velocity addition rules. However, with Lorentz transformations, the time and space coordinates mix into each other. An important idea in special relativity is that time and space should be treated on the same level, unified together into space-time. Because of this, it's easy to see that Schrödinger's equation for single particle position wave functions does not transform relativistically in space-time, because it has a first derivative in time and a second derivative in space. So space and time are not treated on the same level. If you like, you can try transforming the t and x variables in Schrödinger's equation using a Galilean transformation, and you'll find that the result still looks like Schrödinger's equation. On the other hand, the Lorentz transformations will change the form of Schrödinger's equation. This contrasts with Maxwell's equations for electricity and magnetism, where time and space have the same number of derivatives. Maxwell's equations retain their form when we transform them with Lorentz transformations, so they are compatible with special relativity. Also, just as special relativity unites time and space into a single four-dimensional object called space-time, energy and momentum are also united into a single four-dimensional object called four-momentum. The lengths of the four-position and four-momentum vectors are normally measured using a distance function called the Minkowski metric, which is given by this matrix here denoted by eta. The Minkowski metric is important in special relativity because it is unchanged by Lorentz transformations. The Minkowski length of the four-position vector is the spacetime interval S, and the Minkowski length of the four-momentum vector is the object's rest mass m. These quantities are invariant in all coordinate systems. Now let's talk about classical field theories. When you first start learning Newtonian physics, you usually learn it in the language of forces acting on particles. For example, we can calculate the gravitational force of a planet on a small mass, or electric forces between charges, or the magnetic force of a current-carrying wire on a charged particle. However, it's common to take these particle theories and upgrade them to field theories. For example, instead of calculating the forces for a ton of different objects around a planet, we can associate a gravitational field with the planet, which is defined everywhere in space and time, and use that to calculate forces instead. We can do something similar with electric fields and magnetic fields. Fields can be further abstracted to potentials, which are also defined everywhere in space and time. We can derive the fields related to forces by taking derivatives of potential fields. We can even find that these fields have a life of their own. For example, the electromagnetic field can carry energy through space, in the absence of any sources such as electric charges or current. These electromagnetic waves are what light is. When dealing with advanced physics problems, it's common to use the Lagrangian formulation of mechanics, where the Lagrangian is equal to a particle's kinetic energy minus its potential energy. We can plug the Lagrangian into the Euler-Lagrange equations to get the equation of motion for the particle. Loosely speaking, this is a more abstract version of Newton's F equals ma, where forces are replaced with gradients of potential energies, and m times a is replaced with the time derivative of momentum. A basic example is the simple harmonic oscillator, which is a mass on a spring. The kinetic energy of the mass is 1/2 times mass times velocity squared. And I'm using x dot to denote a time derivative of the position x. And the potential energy is 1/2 times the spring constant k times x squared, where x is the displacement from the neutral position. Plugging this into the Euler-Lagrange equation, we get that the spring force negative kx equals mass times acceleration, which is Hooke's law. This has sinusoidal solutions. This partial derivative of the Lagrangian with respect to x dot is often called the canonical or conjugate momentum p, which often gets used in Hamiltonian mechanics. In this case, p is just mass times velocity. It's possible to combine a bunch of simple harmonic oscillators into a continuous scalar field. We can start by taking two oscillators, labeled 1 and 2, and tying them together with a rubber band. Each oscillator gets its own kinetic energy term and its own spring potential energy term. There's also a coupling potential energy term for the rubber band that depends on the difference of the mass positions and an elastic constant kappa. If the x positions are the same, this term does nothing. But if there's a difference in the x positions, there is a restoring force that pulls the masses back together. So the Lagrangian for this system looks like this. Using the Euler-Lagrange equations for x1 and x2, we get two coupled equations of motion for the two masses, which can be written as this matrix equation. Now, coupled equations that mix x1 and x2 are difficult to solve. However, something happens if we look for the eigenvectors of this matrix. We get a solution vector that is directly proportional to the acceleration, which has an easy solution. These solutions are called normal modes, or eigenmodes. The first eigenvector is 1, 1, with an eigenvalue of negative k, and the second eigenvector is 1, negative 1, with an eigenvalue of negative k plus 2 kappa. The first eigenvector gives a normal mode solution where the two masses move together. The second eigenvector gives a normal mode solution where the two masses move in opposite ways. Note how the eigenvalues correspond to the solution frequencies. Since these two solutions are completely independent, we can add them together in arbitrary linear combinations to get a general set of solutions for the system. If we continue to add more and more oscillators, each labeled with a position xi, where I is an integer, we get an infinite field of oscillators. Usually we turn this system on its side so that the oscillators move in the phi direction. And x becomes an axis for identifying the location of a specific oscillator. Phi of x gives the height of the oscillator at location x. Since x is a continuous variable, we have to imagine these oscillators are infinitely close together. It becomes less useful to talk about the total kinetic energy of an entire field. Instead, we talk about kinetic energy density. The kinetic energy density is just the amount of kinetic energy of masses in 1 unit of space. We can use the standard kinetic energy formula 1/2 mv squared. But here, the velocity is the time derivative of the field amplitude. So this is a function that measures how fast a mass is shaking at a given x location. There's also the potential energy density, which is the amount of potential energy in the masses per 1 unit of space. There's the spring potential energy, which is 1/2 k times the squared amplitude of the field, relative to the neutral position. There's also the potential energy of the rubber bands joining the masses together, which is now given by a gradient term, which measures the separation of neighboring masses in the phi direction. Now, many sources do a few redefinitions of the terms here. The elastic constant kappa is often set equal to the mass m. And the field phi is often redefined as phi tilde, using a scaling factor of the square root of m. This allows the m value to be absorbed into the field amplitude. And this k over m term is often defined as a new mass term, m tilde squared. So you'll often see scalar fields defined with these formulas for the kinetic and potential energy densities. Although from now on, I'm going to stop writing the tildes in these formulas. So when we move to field theory, our Lagrangian formula from before gets replaced with a Lagrangian density formula, where all the quantities are densities per unit of space. We also get a field version of the Euler-Lagrange equations. Looking at the Lagrangian density for our field of masses on springs, plugging this into the field version of the Euler-Lagrange equation, we get this equation of motion for the field. Just like we saw with the system of coupled oscillators, for this field equation, there are multiple independent solutions of multiple different frequencies. The most basic solution modes are sinusoidal. Here, omega is the wave's angular frequency in time, and k is the wave's angular frequency in space, also called the wave number. K and omega must obey this mass relation here. We can take any linear combination of these solutions with different wave numbers to get another solution. Although, since the wave number k is a continuous variable, the most general linear combination is done with an integral over k. It's also common to write these basic solution modes using complex exponentials instead of sinusoids. If we extend our Lagrangian to a three-dimensional field with y and z directions, we get this equation of motion, which is called the Klein-Gordon equation. And just as we defined canonical momentum p for individual particles using a derivative of the Lagrangian, we can also define the canonical field momentum density pi using a derivative of the Lagrangian density. In the case of the Klein-Gordon field, the momentum density just measures how fast masses are vibrating at a specific location in space. So hopefully you now understand some of the basic ideas in field theory. A field is described by a Lagrangian density, which keeps track of the kinetic and potential energy densities at specific points in the field. The Lagrangian density can be used to derive the equations of motion for the field, and it's often easiest to consider the most basic solutions to this equation, which are the normal modes, and then add these normal modes together in a linear combination to get a more complicated field solution. Now, one last thing, I've talked about solving problems using the Lagrangian formulation of mechanics, but I should also mention the alternative Hamiltonian formulation of mechanics. We can use the Lagrangian L to define a related quantity h called the Hamiltonian like this. This formula converts equations that use position and velocity into equations that use position and canonical momentum p. However, in simple cases where the Lagrangian terms obey some specific properties, the Hamiltonian is simply defined as the total energy of the system, which is kinetic plus potential energy. Our coupled oscillator system is an example of one of these special cases, and we can get its Hamiltonian just by starting with the Lagrangian and changing the signs on the potential energy terms, and also replacing x dot with p in the kinetic terms. We can also define the Hamiltonian density in field theory. This converts equations to use canonical field momentum pi. Again, in the simplest cases, the Hamiltonian density is just the total energy density of the field. So for the Klein-Gordon field, we can get the Hamiltonian density just by starting with the Lagrangian density and changing the signs on the potential energy terms, and also replacing phi dot terms with canonical field momentum density pi. We'll see the Hamiltonian and Hamiltonian density used later in quantum mechanics. Next, let's take a look at quantum mechanics. Unfortunately, the postulates of quantum mechanics are not as easy to state as the postulates of special relativity. The quantum postulates involve a lot of terminology like Hilbert spaces, Hermitian operators, and expected values. But I'll try to review the most important concepts in quantum mechanics now. Many of these key concepts will carry over to quantum field theory. In classical mechanics, the state of a particle is given by its position and momentum, basically where it is and where it's going. The state of the particle then evolves in time according to Newton's laws. Newton's laws can be reformulated in many different ways, including Hamilton's equations, which use the Hamiltonian H, which is sort of like the total energy of the system. In quantum mechanics, the state of a system is given by an abstract state vector psi of t. The state evolves in time according to the Schrödinger equation, which contains the Hamiltonian operator h hat. This state vector psi lives in a vector space called a complex Hilbert space, which is denoted with a curly h. A complex Hilbert space has the following properties. Coefficients in linear combinations are complex numbers. There is also an inner product, or dot product, between vectors, which is often denoted like this with angle brackets. And performing this inner product in the opposite order gives the complex conjugate of the original result. Hilbert spaces also have a property called completeness, which basically means we can do calculus and do derivatives and integrals in the ways we expect. In quantum mechanics, the results of measurements are always probabilistic. The probability of the state psi collapsing onto some other state A during a measurement is given by the squared magnitude of the inner product of psi and A. This is called Born's rule. Here we call A a bra vector and call psi a ket vector, since their inner product forms a bra ket. A bra vector is given by the complex conjugate transpose of a ket vector. This operation is also called the Hermitian conjugate and is denoted by a dagger. The result of this bracket is called the probability amplitude for the state transition, and the actual probability value is the squared magnitude of this probability amplitude. In quantum mechanics, observable quantities like position, momentum, and energy are each given a Hermitian operator, with Hermitian meaning the operator equals its own Hermitian conjugate. We use hats over top of the variables to indicate that these are linear operators, not just ordinary real variables. If a particle is in a state with an exactly known position x, we denote this state by the ket vector x. This is an eigenstate of the position operator, which produces the exact known position x as an eigenvalue. Similarly, we can also get exact momentum eigenstates for the momentum operator and exact energy eigenstates for the Hamiltonian operator. It can be shown that since these operators are Hermitian, their eigenvalues for the measurable quantities are always real. Also note that since it's impossible for one position eigenstate to collapse onto a different position eigenstate, the inner product of two different position eigenstates is 0. We can summarize the inner product of position eigenstates using the Dirac delta, which is 0 everywhere except when the positions are the same. If a general state psi of t is not an exactly known position eigenstate, we can still expand the psi ket as a linear combination of position eigenstates, where the coefficients on all the kets are the probability amplitudes for collapsing onto that specific position eigenstate. Since x is a continuous variable, we should really write this sum as an integral over all possible position states, where the probability amplitude for each position is given by this function psi of t in x. This is also called the position wave function. If we take this expansion and act on it using a position bra vector, this inner product becomes a Dirac delta, which says that this integral is 0 everywhere except when x tilde equals x. So this inner product of the state psi of t and a position eigenstate x is another way of expressing the position wave function psi of t in x, which gives the probability amplitudes for each x position. If we take the Schrödinger equation and apply a position eigenstate bra vector, we see the position wave function also obeys the Schrödinger equation. I'll say that I am skipping some steps here for pulling the Hamiltonian operator out in front of the bra, but there's a video by Quantum Sense that explains how to do this, and I've linked it in the description. Even if the exact position x is not known, we can still find the expected value of x by performing a weighted average over all possible x positions, weighted by their respective probabilities. This expression can be rewritten in several different ways. Now, I want to stress that the true Schrödinger equation is about the time evolution of the abstract state vector psi of t. The position wave function version of the Schrödinger equation is just one possible representation of the Schrödinger equation in the position eigenstate basis. We could just as easily apply momentum eigenstates to the psi of t state and get the momentum wave function version instead. So the Schrödinger equation is really about the time evolution of the state vector psi of t. The key idea behind the Schrödinger equation is the equivalence of the Hamiltonian operator and the time derivative operator times IH bar. With some rearranging, this says the time derivative operator is equivalent to the Hamiltonian divided by IH bar. If you watched video 16 on Lie algebras, you'll know that exponentiating a derivative operator gives a translation operator for functions. The proof of this involves the Taylor series, and you can pause if you want to go through it. So if we have a state vector psi of t, and we operate on it with e to the delta t times the time derivative operator, we shift the state psi of t forward in time by delta t. We call this exponential the time evolution operator, and we denote it by u. Now, a key property of the time evolution operator is that it must be unitary, meaning its Hermitian conjugate equals its inverse. Here's why. At any given time, the state psi of t should have a length of 1. This indicates the total probability of all outcomes is 1. If we move forward in time by a duration delta t using the time evolution operator, the total probability over all outcomes must still be 1. Since the ket state time evolves with u, the corresponding bra state will time evolve with the Hermitian conjugate u dagger. The only way this transformation keeps the length of psi unchanged is if u dagger and u cancel with each other. So this means u dagger must equal u inverse. So since u dagger equals u inverse, the time evolution operator u is a unitary operator. This unitary property guarantees that probability is conserved over time. This is a core principle in quantum mechanics. I will say that, technically speaking, it's actually the squared magnitudes of state inner products that we want to preserve over time. And technically speaking, there's another type of operator called an anti-unitary operator, which also achieves this. However, the time evolution operator u is unitary, so I'm not going to worry about anti-unitary operators in this video. Now, we can relate this unitary property back to Schrödinger's equation if we look at generators. When a group transformation can be written as an exponential of a parameter times an object g, we call g the transformation's generator. We've seen that the time derivative operator d by dt is the generator for time evolution, also called time translation. However, it's a fact from classical physics that the Hamiltonian, which is sort of like energy, also generates time translations. I'm not going to go into the details here, but you can once again check out Quantum Sense's video on this in the description if you want to learn more. Quantum Sense has a whole playlist on the fundamentals of quantum mechanics that I highly recommend. Anyway, since d by dt and the Hamiltonian both generate time translations, it's tempting to set them equal to each other. However, there are a couple problems with this. First of all, I proved in video 17 that the generators of unitary transformations must be anti-Hermitian, meaning they equal the negative of their Hermitian conjugate. You can pause here if you want to see the proof. Now, we've already declared that operators that correspond to physical observables like energy must be Hermitian, since those give real eigenvalues. So the Hamiltonian operator is Hermitian, not anti-Hermitian. But we can fix this by including a factor of the complex I, which picks up an extra negative sign when you take its Hermitian conjugate. So I'm going to replace the operator h with h over I, which is an anti-Hermitian operator. The second problem is that the units in this equation don't match. We have 1 over time on one side and energy on the other side. So I'm going to include a constant h bar with units of energy times time to make the units work. The result is the essence of the Schrödinger equation, that the time derivative operator equals the Hamiltonian operator divided by I h bar. Both of these are generators for the unitary time evolution operator, so they are equal. This might look more familiar as Schrödinger's equation if we multiply both sides by I h bar and apply it to a state vector. And so this is what the Schrödinger equation is all about. It says that the time evolution generator is anti-Hermitian, and so this generates a unitary time evolution operator, which guarantees that total probability is preserved over time. Now, I mentioned that classical mechanics tells us energy generates time translations. It's also true that momentum p generates space translations in x. This means for position wave functions, where the x operator is simply the x variable, the momentum operator divided by I h bar will give us a generator for space translations, which is the partial derivative of x. It's also true in classical mechanics that position x generates momentum translations in p. So for momentum wave functions, where the momentum operator is just the p variable, the position operator divided by I h bar will give us a generator for momentum translations, which is the partial derivative of p. This procedure of taking classical variables and replacing them with their quantum operators is called canonical quantization, because we're using the canonical variables x and p from Hamiltonian mechanics. This is the standard procedure we use to turn a classical theory into a quantum theory. Now, these two quantization procedures depend on a choice of position or momentum basis. However, there's a more abstract quantization rule that encompasses both of them, which is declaring that the position and momentum operators do not commute, and have a commutator of I h bar. This quantization rule does not depend on our choice of basis for states. We'll see this quantization procedure again when we get to quantum field theory. Now, the fact that position and momentum don't commute means there are no states that have eigenvalues for both position and momentum. This means it's impossible to know both the position and momentum of a particle at the same time with exact precision. This is one version of Heisenberg's uncertainty principle. The last topic in quantum mechanics I'll talk about is the quantum harmonic oscillator, which is a quantum system for one particle whose Hamiltonian contains a standard kinetic energy term plus a quadratic potential energy term, similar to a spring on a mass in classical physics. While the energy levels of this system have known wave functions, the wave functions are difficult to solve for. There's an easier way to solve for the energy levels, where we take the x and p operators and use them to define two operators, A and its Hermitian conjugate, A dagger. This can loosely be thought of as changing variables in a 2D plane from a pair of real numbers x and y to a pair of coordinates given by a complex number z and its complex conjugate. These new operators A and A dagger have a commutator of 1, or the identity operator. This lets us rewrite the Hamiltonian in a much simpler form, where the number operator n hat gives an integer eigenvalue n for the nth energy eigenstate. The energies of these eigenstates are the eigenvalues of the Hamiltonian operator. The ground state at n equals 0 has a non-zero energy of 1/2 h bar times omega. And from there, each additional energy level gains h bar times omega in energy. The A dagger and A operators are called raising and lowering operators, or ladder operators, because they help us move between the different energy eigenstate vectors. We'll see later that understanding the quantum harmonic oscillator is fundamental to understanding quantum fields, so keep this in mind for later. I'll quickly mention that the approach of evolving the state psi forward in time using the time evolution operator u is called the Schrödinger picture. We can instead choose to keep the states constant and evolve observable operators in time instead using u dagger and u. This is called the Heisenberg picture, and it has more obvious parallels with the Hamiltonian formulation of classical mechanics, where Poisson brackets are replaced with commutators. So we've gone over the three areas of physics that come out of Newtonian physics: special relativity, quantum mechanics, and classical field theory. Now let's start uniting them. First, we'll look at relativistic field theory. I've already said that the Maxwell equations from electricity and magnetism are consistent with special relativity, because the form of the equations doesn't change under Lorentz transformations. So they are relativistic field theories. However, the field theory formulation of Newtonian gravity is not consistent with special relativity. Unlike Maxwell's equations, there is only one Poisson equation for gravity, and there are space derivatives but no time derivatives. This equation also changes form under the Lorentz transformations. Newtonian gravity acts instantaneously everywhere in the universe, unconstrained by the speed of light. And also, forces look different depending on which Lorentz-boosted frame you choose due to the effects of length contraction. So it is not a relativistic field theory. To fix this problem, we need to invent general relativity, but we're not going to worry about that here. Instead, we're going to take a look at some of the different types of fields that can exist which are compatible with special relativity. In particular, we'll look at Klein-Gordon fields, which are scalar or spin-zero fields, Dirac fields, which are spinor or spin-1/2 fields, and Procca fields, which are vector or spin-1 fields. If you take the Procca field equation and set the mass to 0, you get the Maxwell fields we know from electricity and magnetism. We've already seen how visualizing a field of coupled masses on springs gives us the Klein-Gordon Lagrangian, whose equation of motion is the Klein-Gordon equation. Now, let's take a quick look at the Maxwell equations for a vector field. Now, this version of the Maxwell equations might look different than the versions you're used to. This capital A is a 4-vector field with 4 components, and this is called the electromagnetic 4 potential. It's made up of 1 electric potential component and 3 magnetic potential components. As I said before, we can take derivatives of potential fields to get force fields. And this combination of derivatives of A gives us the Faraday tensor F, which is a 4x4 matrix that combines the electric and magnetic fields into a single object. So this version of the Maxwell equations, written either with A or F, is equivalent to this pair of the more familiar Maxwell equations, but with the source charges and currents set to 0. Recall that we can get the Klein-Gordon equation by starting with the Klein-Gordon Lagrangian density and putting it through the Euler-Lagrange equations. Similarly, these Maxwell equations can also be derived from this Maxwell-Lagrangian density, if we put it through the Euler-Lagrange equations. If we want to take source charges and currents into account using the 4-current J, we can use this modified version of the Lagrangian density, which gives Maxwell equations with source charges and currents included. Now, waves in the electromagnetic field, which are light waves, have no mass, so there is no mass term in the Maxwell-Lagrangian density. However, we can include a mass term if we want, and this gives us the Procca-Lagrangian density, from which we can derive the Procca equation. The Procca equation describes massive vector fields. I'm not sure if this has any applications in classical physics, but in quantum mechanics, this describes the W and Z boson fields involved with the weak interaction. There is also the Dirac equation for modeling a field of spinor objects, and this can be derived from the Dirac-Lagrangian density. Again, I'm not sure if anything in real life is modeled by a classical spinor field, but we can still consider what a classical spinor field would look like mathematically. In quantum mechanics, this will help us describe the spin 1/2 matter particles. The key idea with these classical fields is that we can know the exact position and momentum of every part of the field at all times. This is unlike quantum field theory, where the uncertainty principle places limits on what we can know about the field positions and momenta at the same time. Each of these classical fields has a quantum equivalent, where the field variables become quantum operators, and we'll talk about this later. Now let's look at relativistic quantum mechanics. Now, the correct way to generalize quantum mechanics to include special relativity involves quantum fields. But historically speaking, physicists did not understand the need for quantum fields immediately. Instead, early attempts at combining quantum mechanics with special relativity focused on trying to make a relativistic version of the position Schrödinger equation. We're going to see that this leads to an inconsistent theory, but I'm going to go through it anyway for historical reasons. Now, I mentioned before that the true Schrödinger equation gives the time evolution of an abstract state vector. However, if we apply a position bra vector, we get the position wave function version of the Schrödinger equation for a single particle. This might trick you into thinking that the position wave function is a space-time field, similar to the electric field, because it depends on time and space. But this is not true. If we had 2 particles, we would use a bra state vector with 2 particle positions, which would result in a wave function with 2 x-value inputs, 1 for each particle. And for 3 particles, this would involve 3 x-value inputs. So quantum wave functions do not live in our standard 4-dimensional space-time. Wave functions live in an abstract state space that can use any number of variables required to describe the state of the system. But again, for historical reasons, let's try to generalize the position Schrödinger equation so that it is compatible with special relativity. Using the standard kinetic energy and potential energy terms from classical physics and applying the quantization rules, we see that the Schrödinger equation for a single particle has a first derivative in time and a second derivative in space. And the equation will change form if we use a Lorentz transformation, which means it is not compatible with special relativity. We can try to fix this by starting instead with the mass-energy-momentum relation from special relativity, and applying quantization rules to that instead. Note that this doesn't contain a potential energy term, so we're ignoring potential energy here. Since energy and momentum are both squared in the original equation, time and space both end up with second derivatives in the quantized equation. After quantization, each term has a factor of I(h bar) all squared. This allows us to pull out negative h bar squared in front. These negative signs inside the brackets can be ignored since they square to +1. This gives us an equation for a wave function where both time and space have second derivatives. We can rewrite these derivatives using Einstein summations with the Minkowski metric eta. We can then bring the terms to one side and use the metric to raise one of the indices on a derivative. This actually gives us the Klein-Gordon equation, but for the position wave function of a single particle. This second derivative operator is sometimes written using a square symbol, called the D'Alembert, and we often choose units where the speed of light c and h bar are 1. The Klein-Gordon equation does obey special relativity and Lorentz transformations. This is interesting because we have now arrived at the Klein-Gordon equation using two different approaches. The first was a 100% classical field inspired by masses on springs, where the exact position and momentum of every part of the field is known at all times. Now we have the Klein-Gordon equation representing the wave function of a single particle, where the wave function is related to finding the position of a particle at a specific time. This tells us that the Klein-Gordon equation is not really about quantum mechanics specifically. Instead, it's a generic differential equation for a function that obeys relativistic physics. However, the Klein-Gordon equation has some problems when applied to quantum mechanics, as it can lead to negative probability densities, which doesn't make any sense. To see why this happens, let's compare the Schrödinger equation and Klein-Gordon equation for position wave functions. The Schrödinger equation has a first-order derivative in time, and the Klein-Gordon equation has a second-order derivative in time. This means that for the Schrödinger equation, if we specify the wave function at an initial time t0, this will completely determine the wave function's evolution over time. For the Klein-Gordon equation, we need to specify both the wave function and the wave function's time derivative at an initial time t0 in order to determine the wave function's evolution over time. This freedom to choose the wave function's initial derivative means the wave function has no probabilistic interpretation, as we'll see shortly. For the Schrödinger equation, the squared magnitude of the wave function does work as a valid probability density, because it is always non-negative, and it also obeys a continuity equation, so probability is conserved. This means that the total probability over all space does not increase or decrease over time. For the Klein-Gordon equation, the squared magnitude of the wave function is non-negative, but it is not conserved. There is a conserved quantity that we can define, but it can be made to be negative, because we are free to choose the initial values of both psi and the time derivative of psi to give us a negative number in this formula. So it seems like the Klein-Gordon equation is a failure for relativistic quantum mechanics. Dirac tried to fix the failures of the Klein-Gordon equation by finding an equation with only a first derivative in time to prevent the probability density from becoming negative. Dirac tried to fix this by trying to find a kind of square root of the Klein-Gordon equation, and factoring it into two parts involving only first-order derivatives. However, this was only possible if the coefficients involved were 4x4 matrices, which are the gamma matrices. Without realizing it, Dirac invented the CL13 spacetime Clifford algebra we saw in previous videos. If we take one of the factors in this formula and set it to 0, we get the Dirac equation. Since the gamma matrices in this equation are 4x4 matrices, the psi wave function object is actually a 4-component object called a Dirac spinor. The 4 components keep track of the spin-up and spin-down states for both positive and negative energy solutions for a spin 1/2 particle. The good news with this Dirac equation is that there is a resulting quantity that is non-negative and conserved over time, so it can be interpreted as a probability density. The Dirac equation also makes some good predictions, like better predictions for hydrogen atom energy levels, and also predicting the magnetic moment for spin 1/2 particles. However, the Dirac equation still has some problems. The biggest problem is that there are both positive energy and negative energy solutions to the Dirac equation. This means that, in theory, a particle at some energy level could drop down to the next energy level, and then the next one, and on forever, releasing an infinite amount of energy, which doesn't make sense. Dirac tried to fix this problem by proposing that the negative energy states were all already occupied by an infinite number of particles, an argument that was later called the Dirac sea. But this argument is pretty suspicious. So far in our attempts to make a relativistic theory of quantum mechanics, our approach was to claim that the Schrödinger equation was wrong, because it had one time derivative and two space derivatives, and therefore was not compatible with special relativity. We then searched for a relativistic equation that would replace the Schrödinger equation in special relativity, but we kept failing and finding more problems. This is partly because our approach is fundamentally not correct. Remember, the core meaning of the Schrödinger equation is that the time evolution of states is unitary, and so the total probability is preserved over time as the state evolves over time. This unitary time evolution property is fundamentally true in both relativistic and non-relativistic quantum mechanics. And so the Schrödinger equation is true in both relativistic and non-relativistic quantum mechanics. We should not be trying to get rid of the Schrödinger equation when trying to create a relativistic quantum theory. It turns out that, if we want to correctly interpret the Dirac equation, we need to move to quantum field theory, which is where we take classical field theory and apply the rules of quantum mechanics to it. So now let's see how we combine quantum mechanics and field theory together. First, I want to point out that in real-life experiments, physicists have seen that particles can be created and destroyed. For example, an electron and its antimatter counterpart, the positron, can annihilate with each other and create a pair of photons. Or in beta decay, a neutron is converted into a proton, and this creates an electron and antineutrino in the process. So in order to be able to explain these phenomena, we need to be able to allow for quantum states to transition between different particle types, or even different numbers of particles. We're going to have to leave behind the idea of a wave function for a single particle evolving over time, because this does not allow changes in particle type or particle number. Instead, we're going to take some inspiration from the quantum harmonic oscillator and its raising and lowering operators. We're going to imagine a whole field of quantum oscillators, each with their own ladder operators. And when we excite one of these oscillators, that is the same thing as creating a particle at that location in the field. So we're going to start viewing particles as excitations in a field of quantum oscillators, which is also called a quantum field. Each particle type will have its own quantum field. A key change we need to make is to start interpreting our quantum state psi of t as representing the state of an entire quantum field instead of just the state of a single particle. With a field, we can create and destroy as many particles as we like, because particles are interpreted to be excitations in the field. To see how quantum fields work, let's go back to classical fields. In classical physics, we made a classical field by joining two classical oscillators together and then joining together more and more oscillators until we got an entire classical field of oscillators. To get a quantum field, we do something similar. We start by joining two quantum oscillators together and then join together more and more until we get an entire field of quantum oscillators, which we call a quantum field. Let's start with a pair of quantum harmonic oscillators, labeled 1 and 2. Each oscillator has its own quantum state psi, along with its own operators for position, momentum, and raising and lowering energy states. When combining systems together in quantum mechanics, we use the tensor product. So the state of the combined oscillator system lives in the tensor product space of the two original systems' state spaces. So we could, for example, label coupled oscillator states using two position labels, which would be the tensor product of two position eigenstates for the individual oscillators. This represents a state where the positions of the two oscillators are exactly known, but the momenta for the two oscillators is completely unknown. We can similarly define a state where both momenta are exactly known, but the positions are completely unknown. We can define two position operators, x1 hat and x2 hat, which act on the combined position eigenstate, and return the oscillator positions as eigenvalues. To be technically correct, x1 hat is actually a position operator tensored with an identity operator. When this acts on the combined position eigenstate, the position operator acts on the first oscillator state, and the identity operator acts on the second oscillator state. The position operator returns the position eigenvalue, and the identity operator leaves the state unchanged. The overall returned eigenvalue is the position of the first oscillator. We have a similar tensor product definition for the second position operator, as well as the two momentum operators. We can similarly define raising and lowering operators, which raise and lower the energy states on each individual oscillator. Now, a key idea here is that we can know the positions of both oscillators exactly at the same time. Mathematically speaking, this means the commutator of the x1 and x2 position operators is 0. We can verify this by writing the position operators explicitly using tensor products, and use the tensor product rule of applying left elements to left elements and applying right elements to right elements. We see the terms cancel, and so the commutator is 0. This means that there are states that have simultaneous eigenvalues for both the x1 and x2 operators. Similarly, we can know both momenta of both oscillators at the same time, so the two momentum operators commute. It's also possible to know one oscillator's position exactly and know the other oscillator's momentum exactly. So operators from different oscillators always commute. It's only the position and momentum from the same oscillator which cannot be known together at the same time. So these commutators are non-zero. The same is true for the commutators of ladder operators. We can summarize these commutator relations using the Kronecker delta, where the I and j indices indicate the 1 and 2 labels for the oscillators. Now, the Hamiltonian for our oscillator system is the same one we saw in classical physics, with kinetic energy terms, spring potential energy terms, and a coupling potential energy term for the rubber band connecting the masses. The only difference is that the x and p variables are quantized and are now non-commuting quantum operators. Now, in classical physics, we saw this system was difficult to solve until we found the normal modes, which were two completely independent solutions we could add together in different amounts to get more complicated solutions. The first normal mode had the masses oscillating together, and the second normal mode had the masses oscillating in opposite directions. We can also use these normal modes in quantum mechanics. We'll define the first mode, big X1, as X1 plus X2, the masses moving together. And the second mode, big X2, will be X1 minus X2, the masses moving in opposite directions. We can have similar definitions for the momenta of the normal modes, big P1 and big P2. I'm also going to scale these formulas by 1 over the square root of 2 for normalization purposes. If we rewrite the Hamiltonian using these big variables, the coupling term disappears, showing that the two normal modes are indeed independent from each other. Also note that the rubber band constant kappa has now been absorbed into the spring constant term. So we now have new spring constants, big K1 and big K2. So the small x's and small p's are used for measuring the positions and momenta of the individual oscillators 1 and 2. But the big x's and big p's are used for measuring the positions and momenta of the two normal modes. Interestingly, you can check that the big x's and big p's obey the same commutation relations as the small x's and small p's. So it's possible to measure the exact positions of both normal modes at the same time, or measure the momenta of both normal modes at the same time. But we can't know the exact position and exact momentum of the same normal mode at the same time, which is why this commutator is non-zero. Also, just as we can define the small a ladder operators for the energy levels of individual masses, we can also define the big A ladder operators for the energy levels of individual normal modes. These allow us to raise and lower the energy states for the normal modes. They also obey the same commutation relations as the small a's. And the Hamiltonian written with the big A operators looks like this, where these number operators count the energy levels of each normal mode. And the normal modes each have their own frequencies, big omega 1 and big omega 2, which define the quantized steps between their energy levels. So we have the original small x's and p's for measuring position and momenta of individual masses. We can use these to define the small a ladder operators for changing energy levels of individual masses. We can also define the big X's and big P's, which measure the positions and momenta of the normal modes of the system. This causes the terms in the Hamiltonian to decouple, making it simpler. And we can define the big A ladder operators for changing energy levels of individual normal modes. The conversion equations between all these operators are given here. Now, we can add more and more quantum oscillators so that we have an infinite collection of oscillators, each with their own x variable denoted by a subscript label I. We usually turn this diagram on its side so that the oscillators move in the phi direction and are labeled with a continuous variable x. So phi of x will measure the extension of the oscillator at location x. This is what we call a quantum field. Just like before, each oscillator has its own quantum state that lives in its own Hilbert space. The quantum state of the entire field lives in a space which is the tensor product of all these individual Hilbert spaces. So the coupled quantum oscillator had two position operators, x1 hat and x2 hat. Our quantum field, with its infinite oscillators, will have an infinite number of position operators phi hat of x, for all the various x locations along the continuous x-axis. For the coupled oscillators, exact position eigenstates were labeled with a pair of position x values, and the x hat position operators would act on this eigenstate to return the position eigenvalue associated with one particular oscillator. For the quantum field, exact position eigenstates are labeled with an infinite number of phi values, basically an entire function of known phi values. The phi hat position operators would act on this eigenstate to return the eigenvalue associated with one particular oscillator. So with the coupled oscillators, the x's are the dynamical variables we measure, and the oscillators are labeled by a subscript number. But for quantum fields, the phi's are the dynamical variables that we measure, and the oscillators are labeled by a continuous x parameter. So in quantum fields, x is no longer a dynamical variable we measure. X is just a label for identifying a position in a field. Also, just as the coupled oscillators had two momentum operators, p1 hat and p2 hat, our quantum field has an infinite number of momentum operators, pi hat of x, for all the various x locations along the continuous x-axis. In the coupled oscillators, exact momentum eigenstates were labeled with a pair of momentum p values, and the p hat momentum operators would act on these eigenstates to return the momentum eigenvalues associated with one particular oscillator. For the quantum field, the exact momentum eigenstates are labeled with an infinite number of pi values. The pi hat momentum operators would then act on this eigenstate to return the momentum eigenvalue associated with one particular oscillator. For the coupled oscillators, I mentioned that the operators are technically tensor products with an identity operator, and this allows them to pick out the specific state in the tensor product to act on. This is also true with quantum field operators, but there are an infinite number of identity operators in the tensor product, since there are an infinite number of oscillator states in the tensor product. For the coupled oscillators, I said it was always possible to know the exact positions and exact momenta of different oscillators at the same time. But it's forbidden to know the exact position and exact momentum of the same oscillator at the same time. So it's only x and p for the same oscillator that have a non-zero commutator, indicated by this Kronecker delta when I and j are equal. It's the same with quantum fields. We can know exact positions and exact momenta of different oscillators at the same time, but it's forbidden to know the exact position and exact momentum of the same oscillator at the same time. So it's only phi and pi for the same oscillator that have a non-zero commutator, indicated by this Dirac delta when x1 and x2 are equal. And just as we can make ladder operators for the coupled oscillators using linear combinations of x and p, we can make ladder operators for the field oscillators using linear combinations of phi and pi, and they obey the expected commutation relations. Now, the Klein-Gordon field has this Hamiltonian density, with kinetic energy density added to the potential energy density. In quantum field theory, all these phi's get promoted to quantum operators. This is called field quantization. It is sometimes called second quantization, but that's a bad name that comes from a historical misunderstanding. Physicists used to think that they had to quantize the energy-momentum relation to get the Klein-Gordon equation, and then quantize it again to get the quantized Klein-Gordon field. But really, we're just taking the classical Klein-Gordon field and quantizing it once. If you recall, we can define conjugate momentum density pi for a field using a derivative of the Lagrangian density. And for the Klein-Gordon field, this field momentum density is just the time derivative of the field amplitude. So we can replace the time derivative of phi hat with pi hat. This makes the Hamiltonian density look more like our coupled oscillator Hamiltonian. Recall that it's easier to understand the Hamiltonian if we rewrite it using normal modes. For Klein-Gordon fields, the normal modes are sinusoidal traveling waves. And remember, the angular frequency omega and the angular wave number k obey this mass relation. For convenience, we can rewrite this cosine as a complex exponential. This lets us split up the factors for time, space, and phase. The phase factor can be absorbed into the overall amplitude, making the amplitude a complex number. If we want to get the original real field back, we can just take the real part of this complex field. Also, while the field technically depends on both time and space, for the remainder of this video, we're going to take the special case where all the operators act at the same constant time. So we're going to be ignoring the time parameter of the field. Now, with the coupled quantum oscillators, we combined the two oscillator position operators in linear combination using the normal mode coefficients to get the big X position operators for normal modes. We can do something similar for oscillators in the Klein-Gordon field. We can combine the various phi position operators together using normal mode coefficients given by these complex exponentials. Since x is a continuous variable, the linear combination over x is done using an integral over x. The result is the operator big phi, which measures the position of a specific normal mode with wave number k, which is related to the mode's momentum p using h bar. This transformation between operators for individual oscillators and operators for entire normal modes is the Fourier transform. The transformation between small x and big X in the coupled oscillators was also a Fourier transform, but this is less obvious since there were only two terms in the sum, which gives coefficients of +1 and -1. We can use a similar Fourier transform formula for the pi momentum operators to get the big pi operator, which is the field momentum operator for the normal mode with wave number k. We can also get the inverse formulas that change from big phi and big pi back to phi and pi. These inverse transformations have opposite signs on the exponentials. Also, in the convention I'm using, both of these Fourier formulas have a factor of 1 over the square root of 2 pi in front. Some other sources will use a convention where both of these factors are on the inverse formula only. It's also worth noting that if we take the inverse Fourier transform formula and then sub in the Fourier transform formula for big phi, we should get the original small phi result back again. We can prove this is true by grouping these exponentials together, and then using the property that this integral over an exponential of k is a definition of the Dirac delta. This allows us to remove one of the integrals and replace x tilde with x, showing that we do indeed end up with the original phi hat operator. This definition of the Dirac delta works because if the x and x tilde values here are different, the complex exponential becomes a sinusoid, and this integrates to 0 if we integrate from negative to positive infinity. But for x equals x tilde, the exponential in the integral becomes 1, and we end up with an infinite spike, just like a Dirac delta. Now, since we're using complex numbers in this Fourier transform, I do have a few notes to add. First, the big phi and big pi operators are no longer Hermitian operators because of the use of complex numbers. So their eigenvalues are now complex numbers. This is because the amplitudes in front of complex waves contain both magnitude information and phase information. Because of these complex numbers, when writing the Hamiltonian density, instead of writing the squares of operators, we're going to write the squared magnitude of operators, which is equal to the dagger of the operator times the operator itself. Now, our phi and pi operators still represent real fields with real observable eigenvalues, so they are still Hermitian operators. As a result, it can be shown that their Fourier transforms big phi and big pi have a special property where their Hermitian conjugate equals the same operator, but with the negative wave number. This is a property that will come up later. Also, you can pause on this slide to see the proof of how to get the commutator of big phi and big pi. Note that the Dirac delta here has a plus sign between the k's. So with the coupled oscillators, we liked the normal mode operators because they gave a simplified Hamiltonian and got rid of the coupling term. The same is true for the Klein-Gordon Hamiltonian density. So what we'd like to do is take small phi and pi, which are functions of position x, and replace them with big phi and pi, which are functions of normal mode wave number k. To do this, I'm going to go through a few properties quickly. First is Parseval's theorem, which says that the integral over the squared magnitude of a function is equal to the integral over the squared magnitude of its Fourier transform. This applies to both phi and pi. This is true because the Fourier transform is a unitary transform, which means it's kind of like a rotation that doesn't change the norm of functions. You can pause here to view the proof of Parseval's theorem if you want. Parseval's theorem will help us transform the first two terms in the Hamiltonian density, but we also need to transform the coupling term with the x derivative of phi. If we take this derivative and replace phi with the inverse Fourier transform, the x derivative only touches this complex exponential, which brings out a factor of ik in front. If we take the squared magnitude of this, we end up with the squared magnitude of k in the integral, which is really just k squared since k is a real number indicating the wave number. Now let's take our Hamiltonian density and integrate it over x. Using Parseval's theorem, we know we can change the first two terms into integrals over k of the Fourier transformed functions. And we get a similar result with the x derivative term, but we can replace the derivatives with factors of k in front like we saw before. If we look at all the terms in this integral over k, this gives us a new Hamiltonian density operator, which I'm calling h tilde hat, although I will often leave out the tilde later in this video. This measures energy density for the normal mode with wave number k. Also, using this mass relation, we can rewrite m squared plus k squared with the angular frequency omega squared, which is a function of k. As promised, we can indeed see that the Hamiltonian, when written with the normal modes, is simpler because the coupling term has disappeared. And again, with the coupled quantum oscillators, there was one last change of basis to the big A's, which gave us the big A ladder operators for specific normal modes with specific frequencies. We can define similar big A operators for our Klein-Gordon field, and these let us create or destroy normal modes with wave number k in our field. Notice that these formulas involve negative k as an argument here. This is related to the fact that the big phi and big pi operators are non-Hermitian. You can pause the video here if you want to see how to rewrite the Hamiltonian density using big A operators. It can also be shown that the big A operators obey these commutation relations. So when people talk about general solutions of the Klein-Gordon field, you'll often see phi of x expressed using an integral over all possible normal modes. And then big phi is usually rewritten as a linear combination of the big A ladder operators. After splitting the integral into two and flipping some of the signs for k, we get this final solution here for phi of x expanded out in terms of normal mode ladder operators. There's also a similar general solution for pi of x written like this. For coupled oscillators, we also defined the number operator n for counting the energy levels of a specific normal mode I. For quantum fields, we can define a similar number operator for counting the energy level of the normal mode with wave number k. The physical interpretation of this is that n hat counts the number of particles with wave number k. If we include a factor of h bar, this lets us count the number of particles with momentum p in the field. Now, there is a well-known problem with writing the Klein-Gordon Hamiltonian density in terms of number operators. We get this term involving a Dirac delta of 0, which gives infinity. This seems to be implying that the Klein-Gordon field has an infinite energy density even when there are no particles present. For practical calculations, we ignore this term since we only care about energy differences. And since this infinite term appears in both the initial and final states, it will cancel out on both sides. There's a lot more you could say about this term, but I'm not going to bother talking about it in this video. So to sum up, we have position and momentum operators for each oscillator, phi and pi. We have the small a ladder operators for changing individual oscillator energy levels. We also have big phi and big pi operators for the normal mode positions and momenta. And we also have the big A ladder operators for changing energy levels of the normal modes. And these are the equations that relate them. Most quantum field theory textbooks tend to focus only on the original operators and the normal mode ladder operators, since these are the operators most useful for calculations. But personally, I find it confusing when the other operator types are not included in the explanation. Now remember, in quantum field theory, we interpret particles as excitations in a field. The small a ladder operators allow us to create and destroy particles at a specific position. And the big A ladder operators allow us to create and destroy particles with a specific momentum. So we can apply these small a creation operators to the vacuum state to create particles at specific positions. Since creation operators at different locations commute, the order of creation doesn't matter. Applying the creation operator at the same position twice will create two particles at that position. The same is true for the equivalent big A momentum operators and their states. Normally, we would have to write position or momentum eigenstates using an infinite number of labels, specifying how many particles are in each possible position or momentum state. But we usually leave out the states with 0 particles and only write the labels for states with a non-zero number of particles. Just like in ordinary quantum mechanics, we can evolve these quantum states forward in time using the time evolution operator, given by exponentiating the Hamiltonian operator for the field. But this process ends up being a lot more complicated for fields, since the Hamiltonian of a field is the integral of the field's Hamiltonian density. I won't be discussing how to calculate this in this video. Now, if you'll recall in single particle quantum mechanics, each possible position eigenstate x of a particle had a probability amplitude associated with it, which was the value of the wave function psi of t in x for that position. We got this probability amplitude by projecting the bra position state x onto the quantum state psi of t, and the wave function psi of t in x obeys the Schrödinger equation. The same is true for quantum fields. A field eigenstate phi is a state where the exact field value of every oscillator in the field is exactly known. Each possible field eigenstate phi of a field has a probability associated with it, which is the value of the quantum wave functional psi of t and phi, for a given field state phi. We're saying psi is a functional because it takes a function phi as input and returns a complex number. We get this probability amplitude by projecting the bra field state phi onto the quantum state psi of t, and the wave functional psi of t and phi obeys the Schrödinger equation. So it's important to know the Schrödinger equation still applies in quantum field theory. But the wave function does not live in position space. It lives in the space of all possible fields. And the Schrödinger equation makes sure the time evolution is unitary, so that probabilities are preserved over time. Now, this wave functional is usually too complicated to deal with directly, and we usually have to work with normal mode field solutions instead to simplify things. But conceptually, the wave functional for the quantum field does exist, and it does obey Schrödinger's equation and evolves according to unitary time evolution. Also, just as we can write the momentum operator p hat using an x derivative in position space, we can also write the field momentum density operator pi hat using something called a functional derivative of the field phi. But I'm not going to discuss that here. So the key takeaway I want you to get from this video is that quantum mechanics and quantum field theory are not two totally different theories. Both involve a quantum state psi of t that evolves according to Schrödinger's equation and obeys unitary time evolution. It's just that the states for quantum mechanics involve individual positions or momenta for individual particles, whereas states in quantum field theory correspond to possible field configurations or field momentum configurations for an entire field of quantum oscillators. The inner product of these eigenstates with the state psi of t gives the probability amplitude of the state psi of t collapsing onto that eigenstate. So hopefully that gives you an idea for what a quantum field is. Now let's bring all of this together into relativistic quantum field theory, which most people just call quantum field theory. We've already learned about several relativistic classical field equations: the Klein-Gordon equation for scalar fields, the Dirac equation for spinor fields, and the Proca equation for vector fields. We can also calculate the field momentum density for each of these fields using the usual formula. Now, if we want to quantize these fields, we can take the field and field momentum variables and impose the quantization condition, which forces the fields and field momenta to obey commutation relations, or anti-commutation relations in the case of the Dirac equation. After quantization, the Lagrangian and Hamiltonian densities are now operators written in terms of the field operators. We can also change the operator basis to the creation and annihilation operators, which let us create and destroy particles in the field. Although I should mention that creating spinor and vector particles is a bit more complicated because these are multi-component objects. Also note that I'm dealing with the full 3 dimensions of space in these formulas, and so the formulas on this slide use the 3-dimensional version of the Dirac delta function, and the Fourier transform formulas use a factor of 1 over the square root of 2 pi taken to the 3rd power. It's also possible to make different fields interact with each other by introducing additional terms in the field Lagrangian or Hamiltonian densities. For example, this term couples together the photon field A and the electron field psi in quantum electrodynamics, allowing photons to interact with electrons through the electromagnetic force. These interaction terms can make the field equations of motion nonlinear, meaning the sum of 2 solutions is no longer a valid solution. However, the Schrödinger equation for the time evolution of the quantum state is still linear. Now, these are all examples of relativistic quantum fields, but what about non-relativistic quantum fields? The difference between relativistic and non-relativistic quantum fields basically comes down to a speed limit regarding how quickly one part of the field can talk to another part of the field. If there is no speed limit for how fast field disturbances propagate, then we are working with a non-relativistic quantum field theory, and the form of the field's Lagrangian density will remain the same under Galilean transformations. However, if the field disturbances are limited by the speed of light c, we are working with a relativistic quantum field theory, and the form of the field's Lagrangian density will remain the same under Lorentz transformations. We've seen several examples of relativistic quantum fields which are used in particle physics, where particles are often traveling close to the speed of light. However, certain condensed matter systems can be described with non-relativistic quantum fields. For example, the non-relativistic Schrödinger field can be used to describe Bose-Einstein condensates, or superfluids. I want to be clear that this might look like the Schrödinger equation, but psi is not a wave function. It's actually a field operator that represents coupled oscillators in a quantum field, and it obeys commutation relations. Here, the physical phenomena tend to travel much slower than the speed of light, so relativistic effects can be ignored, and a non-relativistic field is sufficient for modeling the physics properly. Now, everything I've talked about in this video approaches quantum field theory using the formulation called second quantization, also called field quantization or canonical quantization. There's an alternative formulation of QFT called the path integral formulation, which is based on the principle of least action, but I'm not going to talk about that here. One very last thing I want to discuss is the spin statistics theorem. The spin statistics theorem states that integer spin particles, like spin 0 scalars and spin 1 vectors, are always bosons. Bosons have the property that identical particles can occupy the same state. Boson creation and annihilation operators obey commutation relations, and bosonic wave functions are symmetric under the exchange of two identical particles, so swapping the particles results in the same wave function value. The properties of superfluidity and superconductivity are explained by this property of bosons that allows identical particles to exist in the same state. The theorem also states that all half-integer spin particles, like spin 1/2 spinors, are always fermions. Fermions are particles that obey Pauli's exclusion principle, where identical particles cannot occupy the same state. This is why no two electrons with the same spin can occupy the same atomic orbital. Fermion creation and annihilation operators obey anti-commutation relations. These anti-commutation relations say that applying a creation operator for the same state twice gives 0. So it's impossible for two identical fermion particles to occupy the same state. Fermionic wave functions are also antisymmetric, meaning exchanging two identical particles results in an extra negative sign. This means that two identical particles being in the same state will result in a wave function value of 0, which again means that two identical fermions being in the same state is impossible and has probability 0. While the spin statistics theorem is easy to state, it's pretty difficult to prove, and I honestly don't understand the proofs yet, so I won't be proving them here. Now, it can take several weeks, or even months, to learn the theory behind quantum fields in a classroom. But learning to solve quantum field equations can take additional weeks and months. For example, to solve quantum electrodynamics problems that involve electrons, positons, and photons all interacting with each other, you need to learn the method of Feynman diagrams. These are often first presented as cute pictures, but each of these pictures represents a complicated integral that must be calculated in order to compute the final result. The technique of renormalization must also be used for dealing with diagrams that have loops. These Feynman diagrams come from using the time evolution operator on a quantum state. We can write the time evolution operator as the exponential of the Hamiltonian operator, and the Hamiltonian operator can be written as the integral over the Hamiltonian density operator for a given quantum field theory. When this exponential is expanded as a Taylor series, we call it a Dyson series, and the various integrals in this series correspond to Feynman diagrams. The exponent on any given term indicates the number of vertices in the Feynman diagrams for that term. For predicting quark interactions in quantum chromodynamics, it's common to model space as a lattice and run computer simulations to see how the system will evolve over time. Quantum field theory is a bit of a strange subject because it's possible to know a lot about the theory and symmetries of quantum fields, but have no idea how to solve them. Whereas it's possible to know how to solve quantum field systems while not knowing a large portion of the theory. In this video series, I will not be teaching any of these methods for how to solve quantum field equations. Instead, I'm just going to focus on the simpler cases involving a classical Dirac field of spinors where no quantum mechanics is involved, and also seeing how these same solutions to the Dirac equation can be interpreted in relativistic quantum mechanics, and how Dirac spinors keep track of both matter and antimatter for spin 1/2 particles. I will not be looking at the Dirac equation where the quantization procedure has been applied, making it a true quantum field. I'll start going through more careful derivations, solutions, and interpretations of the Dirac equation in the next few videos.